Hi guys, this is Miss Hubbard. I'm going to talk to you about Chapter 2 in the AP textbook. Please read page 27 and 28 about Mono Lake. It's a really interesting story about what happens when they diverted water from this lake. It messed with the food chain because the lake got a lot saltier. So I'd like you to read that, and we'll talk about that one and try to understand what happened there. We're going to talk about systems in chapter 2 and about some chemistry. Remind you guys about some chemistry that you should already know, but I'll review it with you guys. So first of all, we're going to talk about systems, and we talked about that a little bit in chapter 1, and now we're going to go into it deeper. So a system is has interconnected components. And if you change one, you're going to change everything. You're going to affect the other ones. You can have large systems, which would be, for example, the Earth. The Earth has many, many systems as part of it. So you have one large system and you'll have subsystems. And in general, for AP Environmental, we're looking at energy interactions and matter interactions between systems. So to get an idea of what a system is, you can have a small system like a codfish right there. It has, it would be one system. There would be matter and energy going in, matter coming out, and energy being used by the fish. A larger system would be a predator-prey relationship between two fish species, and that would form a system. An even larger system would be where an oceanographer would look at ocean currents and their effects on the fish populations. An even larger system would be looking at many fish populations and human activities related to the fish populations and the laws that govern all that. So that's an even larger system. And as you can see, you have these small subsystems are a part of a bigger, larger system. In the chapter, they're reviewing chemistry with you, and remember, matter has mass and it occupies space. Remember, mass is different than weight, because weight is what happens to what force is acting on the mass. So remember, matter is mass. It's how much stuff something has. That's its mass. And the volume it takes up, the space it takes up, are the two things that define matter. So matter is anything that occupies space and has mass. In this course, we're going to talk about radioactivity as it has to do with in several ways. One way would be for looking at nuclear energy, but in this case, in this chapter, we're really talking about radioactivity and what happens when naturally occurring isotopes decay into other isotopes and the time it takes to do that. Very, very important in environmental work is looking at radioactive isotopes and how they decay, because right now you guys are breathing in different forms, different carbon isotopes, and we know the ratio that's occurring right now in the air and the food that we're taking in. As soon as someone dies, then that ratio is going to change, because you're going to have the carbon-14 decaying into nitrogen-14, and then we can look at that. So we can say how long someone's been dead by this, knowing what the carbon-14 percentages were at the time of the death, and then looking at what we have for carbon-14 now. So we can see how long that person's been gone, or that animal, or that plant. So radioactive carbon dating is very, very important in environmental work. The carbon-14 would be called the parent, and nitrogen would be called the daughter. So we have a parent, which is the beginning material, and the daughter, which is the secondary material. Remember that this number right here is the mass number. It's how many protons and neutrons that carbon has. So generally, most of carbon is carbon-12. It has 6 protons, 6 neutrons. but this one has more neutrons. Remember, an isotope is something that has more neutrons than another isotope. So you can have a particular chemical like carbon, it has different numbers of neutrons, so that would make it have different isotopes, but they're all carbon. They react like carbon. Half-life, I was talking to you a little bit about that just now, is how long it takes for a chemical to change. It's the time it takes for half of the material to be changed into something new. So, for example, carbon-14 has a half-life of 5,280 years. So it takes that long for half of the material to be changed into the nitrogen. So that's what half-life is. So there's two different things to know. The time it takes, that's the half-life, and also remembering that you're losing half of your mass of your material, but it's changing. You're not losing it, but you're changing it into something else. Some elements, when they do this, give off harmful radiation that's going to hurt people, animals, plants, and some give off radiation that doesn't hurt those things, and we'll talk about that when we talk about radioactive nuclear plants and radioactivity when we get to that part. So, like I said, it helps us figure out how long something has been, dead, how long. That's how we figure out, how dinosaurs and all the different eras of the Earth have how long they've taken. We use carbon dating for that. So remember the parts of the atom. So you should have gotten this in chemistry and remembered it. And remember, the nucleus has the protons and the neutrons. The nucleus is positively charged. So you have neutrons that don't have any charge. You have protons that have a positive charge. So when they come together, they make a positive charge in the center of the atom. Most of the atom is empty space, and in the very center is the nucleus. And my friend Rutherford figured that out. So I love that whole thing. And we'll talk about Rutherford all year long because he's my favorite scientist. So we have protons in the center. We have neutrons in the center. These make the mass of the atom. So I was talking about carbon-14. So it has 6 neutrons, and that would have 6 protons, and it would have 8 neutrons to make 14. So the number of protons in the center equals the number of electrons on the outside for a neutral atom. So for carbon, there'd be 6 here, and there'd be 6 on the outside. This is showing nitrogen, so you would have, this has all the 7 electrons on the outside, so there would have to be 7 protons in the inside, and then whatever number of neutrons it would have. Okay, these circles right here are called the shells. So in the first shell of an atom, it can hold 2 electrons. In the second shell, it can hold 8. And then it continues on. The next one, if there was another shell, it would hold 8. So there's a particular number of electrons in each shell. These little electrons really live in something that looks like this, not this. This is an old school called the Bohr atom, the Bohr model of atom, and this is the way we think of the atoms now, that they live in particular shapes. And so these are called orbitals. Okay? So let's look at the periodic table real quick and remind ourselves how that works so we can use it this year. So remember, this group 1 has 1 electron in its outer shell. Group 2 has 2 electrons in its outer shell. Group 3A has 3 electrons in its outer shell. Group 4 has 4 electrons in its outer shell. 5 has 5. 6 has 6. 7 has 7. And 8 is totally filled up, has 8, except for helium can only hold 2 in that small shell. Hydrogen has 1 electron in its outer shell. Helium has 2 in its outer shell. The other thing to remember is that the guys on the left side of the periodic table like to give away electrons. The guys on the right side, the red ones, like to take electrons from other things. So if you have an atom over here hooking up with an atom over here, they're going to be Once the right side guys are going to rip off the left side guys, and that's called an ionic bond. So fluorine is actually able to take an electron from the guys over on this side. Okay. So that's ionic bonding. If they're far apart on the periodic table, then they're ionically bonded. If they're really close together, like carbon dioxide or nitrogen oxide, these guys right here are pretty close together in strength for electronegativity, so they like to make covalent bonds. So when they're close together on the periodic table, remember they make covalent bonds. So anybody around here, usually the guys over here on this side, are going to be bonded. If they're both on the same right side, they're going to be covalently. So carbon dioxide, nitrous oxide, all those kind of things are going to be covalently bonded. The only weirdo here is hydrogen. When hydrogen hooks up with these guys, they make covalent bonds. So that little rule about far apart on the periodic table is a little exception for hydrogen because he likes to be covalently bonded with these guys here. Okay, let's go back to where we were. Alright, so we talked about how atoms are put together. Remember, center is protons and neutrons, outsides are electrons. Most of the atom is empty space. There's about 99% of it is empty space, and then there's a 1% that's in the center, and it's very, very dense, and it's solid. In the center, these guys are so close together that they actually have a different force in between them, pushing them together, and that's called the nuclear force. So if we can break this nucleus, then we get nuclear energy. So there's electronic force with these electrons when they're bonding with other people. That's electrical force, electrostatic. And inside here is nuclear force. So there's two different forces that are affecting an atom. So like I said, if they're far apart on the periodic table, for example, sodium and chlorine, let's look at them. I got sodium and I got chlorine, so they're far apart on the periodic table, so they are going to bond ionically. They're far apart. So chlorine is the more electronegative, so he actually grabs this electron from sodium and brings it over to fill his shell up. So now he's happy he has 8 electrons around it. Remember, atoms are happy when they have a full shell on the outside. Sodium's now also happy because you got rid of this one electron that was in this outer shell, and now if you look at this shell here, this shell's full and happy. So by doing this ionic bonding, they both become happy. This guy has a full shell, sodium has a full shell, and chlorine has a full shell. So that's why ionic bonding works. And then we said that atoms that are close together on the periodic table are going to be covalently bonded. And remember, hydrogen also likes to be covalently bonded with the guys on the right side. So one more time, hydrogen's over here, and oxygen's over here. So this is a weirdo. He actually likes to be covalently bonded with people over here. So the way this makes everybody happy is that hydrogen has 1 electron, but he's sharing one with the oxygen, and this hydrogen has 1 electron and he's sharing it with oxygen, so they both everybody's happy because now oxygen has a full outer shell and hydrogen has a full outer shell of 2. Okay. The way that this is configured, you see how it looks like a little upside down Mickey Mouse. These bonds, the way these are bonded, and because they're not straight across like that, it makes water super unique, and the only reason we're on this planet is because of the shape of water and the unique properties that water attains because of that. So water is amazing, and I'll be talking about that all through the year, but water is so cool because it has this cool shape, and that makes it have a negative side and a positive side, which makes it really super unique. If you look at this side, see oxygen has a whole ton of electrons on the side, so this side feels like it's negative. And then on this side, these electrons are being shared over here, so this side over here is partially positive. So this side is partially negative, and this side's partially positive. So these little water molecules act like little magnets, and it makes them want to stick together, which is called hydrogen bonding. So this is the oxygen right here. These are the hydrogens right here, the hydrogens are positive, so they're going to say, hey, I want to get close to a negative oxygen. So that's what happens. And this makes water really sticky. Water molecules like to stick together like little magnets. And it makes a lot of cool properties, and the only reason we're here on Earth is because of all these cool properties. So that's called hydrogen bonding. They're not actually physically sharing electrons or anything like that. They're just happy to be together because one's positive, one's negative. So opposites are attracting there. One's partially negative and one's partially positive. So like we said, hydrogen bonds are a bond. They're very weak. They're not on the same strength as ionic or covalent, but they are very, very important. Water, because it has that cool shape and it has a partial positive and partial negative side, it's called a polar molecule. Polar means it has two poles, like North Pole, South Pole. That means one side's positive, one side's negative. That's what polar is standing for. So it helps a lot of animals and helps us for water to have cool properties. So as you can see, this water strider, little bug, is able to stay on top of the water because the water is sticking to itself so much that it won't let the legs of this water strider go down through it. So remember the boiling freezing points of water, and these two nice numbers help us stay as living humans, because water on the Earth, the temperature of the Earth is perfect for us to stay within these two temperature ranges and keep us from getting hurt. And also remember, water is very interesting because it has that positive negative side. It's able to become a solvent, and it's able to dissolve stuff. So anything that has a partially positive and negative side, like sodium chloride, a lot of ionic compounds love to dissolve in water. It's very, very good at pulling things in and dissolving them. It's called a universal solvent. The interesting property of water that also helps us live on this planet is that when water, this is liquid water, or ocean water right there, when it's in a water form, it's really compact. But once it turns into ice crystals, it forms this six-sided structure that has hydrogen bonding in between it, and it's much less dense than the liquid water. So ice, being less dense, is able to float on this dense water. So that helps a lot of animals live, because if it was the other way around, then we wouldn't be able to have fish living in iced over ponds and animals able to live in the Arctic oceans. So it's very, very, very cool property of water. Let's talk about acids and bases. Acids, remember, give an H+ ion to somebody else, and base gives off hydroxide ions. And there's several different theories about acids and bases, so this is like the most simplest theory, but there's also other theories that we'll talk about in class. So this is the basic Arrhenius theory that says that acids give off a hydrogen, and base gives off hydroxide ions, OH- ions. The H+ right here, OH- right there. pH is super important in environmental because we want animals, plants, humans to be able to live in the particular water we have. And so we want things to be close to neutral, which means that the H+ are balancing out the OH- in water. So the range, remember, pH goes from 0 to 14. 7 is neutral, and that's good for a lot of plants and animals. If it's got a bigger number than 7, it's going to be basic. If it's got a smaller number, it's going to be acidic. So, like I said, pure water that has nothing in it is going to be pH 7. Seawater's a little on the basic side, which is fine. It's got salt in it, so that makes it a little bit basic. Rainwater is a little bit acidic because when it falls down through the sky, it picks up carbon dioxide, which makes carbonic acid inside the water. It picks up nitrogen and nitrogen oxide things from pollution from any combustion of nitrogen makes NOx's, so that makes nitric acid. So it makes the water, when it comes through the air, pick up those things and become a little bit acidic. This is when it's getting a lot of pollution, then it's going to be way down in this range. And when you drink your Coke, it's going to be down here. Your stomach's in this area. There's some areas on Earth that have very high pHs, so very, very basic, and they can support things. But generally, animals like to be in, near the 6, 7, 8 range. Okay. A chemical reaction occurs when atoms combine together or separate from a molecule. So it's when you're having 2 or more atoms combining or separating from a molecule. So that's a chemical reaction. We know that matter on Earth cannot be created or destroyed. That's the law of conservation of matter, and you've learned that many times, I think, in your classes. And you can't ever disappear matter. You can't destroy it, but you can change its form. So, for example, when you have forest fire, you have all that nice carbon-containing cellulose in the trees. So that cellulose, which has a lot of carbon and a lot of hydrogen and oxygen, changes form from cellulose, which is one big long chemical molecule, into smaller pieces, which would be carbon dioxide and H2O and anything else that might be in that. There might be some nitrogen compounds inside that in those trees. So all those would become oxidized. They have oxygen attached to them, and they would become gases and fly away, and there would be some ash and debris left over. So you're not losing any of the molecules inside there. You're just changing them into different forms. That's conservation of mass. There's 2 classes of chemicals. There's inorganic compounds and there's organic compounds. Inorganic can contain carbon, but it's only carbon plus something else, some inorganic thing like carbon and oxygen. Pretty much carbon and oxygen are going to be your inorganic ones. So you will see carbon sometimes, and that's inorganic. Organic compounds are things that are with carbon. A carbon bonded to a carbon or carbon bonded to a hydrogen. Those are organic bonds. So we have 2 classes of chemicals, inorganic, organic. These are all organic compounds, and they're inside cells. You have carbohydrates, which are your energy storage molecules. You have proteins, which are form enzymes or form membranes, very important proteins. Nucleic acids are the ones that are giving your blueprint for your particular organism, and RNA is producing the proteins that you need. Lipids are fats that are in your body or in a plant, in plants and animals. So you know that the smallest animals are single-celled bacteria, some algae, and then you have multicellular things such as, this is misspelled, this should be brine shrimp. So you have cells, and then you have so this is one cell, and then you have this brine shrimp which has tons of cells in it. And that's what they were talking about in the beginning of the chapter. Mona Lake has these brine shrimp in them. And hopefully we'll be able to use those this year. So that's the first part of chapter 2, and then I'll have a second lecture slides for the second part of chapter 2. So ask me any questions you have, and I'll talk to you soon. Bye-bye.